So in this lecture, we are discuss about some real world cases of the SVMs. And till now, what we have learned, what we have learned. So I am just summarized in this lecture. So first, let's take. So first, let's take one. Let's take first considering the features engine. We are at the starting of this series of lecture. We see how the features engineering and features transformations is more important for SVM as well as for logistic regression. So just first, now we see it, how it is important. Features engineering and features transformation. How it is. So we see that these features engineering and transformation instead of that we implicitly used in logistic regressions, but here we are using internally. That is, implicitly we are not use the features engine implicitly. So in or another language we use this one internally or kernel design. For kernel design purpose, we have used this one to find the right kernel. Okay, and also this thing we also see RPA, radial basis. Okay? This is our default kernel trick RPF. If we had we have no concept of our data sets, we are without any doubt we can easily use this radial basis. We have seen this how features engineering and transfer important on kernel tree. Now the next feature, sorry, next most important thing is decision surface. See. So we see that in a linear in a linear SVM, we see in linear SVM where simple build the hyperplane, we are simple build a hyperplane, but in non-linear SVM, we are simple using the kernel SVM. For non-linear set of data, we are using simple kernel SVM. Linear thing, kernel we have used the kernel SVM. For non-linear sir, for non-linear. Okay. So here what we will see, we see that if our data set lies in d-dimensional point, if our data set lies in xi spaces, by example using kernel tree, we are convert this dimension to d dash dimension, and then where this is our x. Okay, but here, but in this surface, non-linear surface, sorry, in this surface it is non-linearly separable, but in d dash surface we see that it's linearly separable or linearly separable. You see this thing, our main trick of surface how to handle this. Now let's consider the similarity functions, or some we are using the kernel functions as similarity function. or we are using distance function for dissimilar function. We have seen this thing. And for similarity functions, and for similarity purpose function, what we are using? A of for two set of points, k of x. Okay. Kernel we are using, we have to choosing the kernel. For similarity, as the place of similarity, we see the kernel, and there we have see the this function. There we have see the Gaussian sigmoid function, that is on a or another language it is a Gaussian probability, such kind of like Gaussian probability distribution. Okay, what is this kind of norm of x1 minus x2 area to square divided by 2c. I think it whole square, yeah, for both sides. Okay, we have seen these kind of functions in similarity functions. So where we are discussing kernel SBF, RBF functions. We are discussing RBF. We have seen this. Okay. Now the main thing is that interpretability. What the most important thing is features, interpretability and features important. We see in linear regressions, logistic regressions, how to find the most important features. But here we can find it. Interpretability and features important. Okay, we see that. If you just remember, nowhere it is not possible in SVM, mainly in kernel SVM. It is not possible. SVM mainly in if we kernel SVM, in kernel SVM, mainly in kernel SVM, it is not possible to detect the important features important. Okay, features importance for various features. It is totally impossible. Totally impossible. It cannot find the features important. It's impossible. But we can simple by simple using the trick is we know the forward selection method. If we use this kind of technique, we can easily. Plus, this is a long lengthy process. Okay, but simple we cannot find just simple generally. But if we use the forward selection method, if we use the forward selection method, then it is possible in this situation. Okay. Now the main thing is that here outliers. So we see that in soft margin SPM, how it is sensible for outlier. So it is very outlier impact. What is very little. So outlier is totally you can ignore. You cannot consider the outlier in the SPM. Is the most important for a if your data sets there are so much outliers, then SVM is the good one. Very little out. It is less impacted for outlier. Okay. Because of C, we or another language. If we just remember the dual problem of the dual SVM problem, here we are consider only the alphas or support vectors. Example, here we are also considering only the support vectors. Okay? We are only consider the support vector. We are ignoring the non-support vector. This is the another reason. We are totally ignore this non-support. This is the another reason why the outlier is little impact. Because support vectors, that's main matter. And also we see RBF. If you just remember the radial basis functions kernel tree, then simple by using the per sigma, then we can easily handle the outlier. With a small sigma, okay, with a small sigma, so it is easily outlier. We choose the small sigma, then it is most we are taking here. We are considering for a small. We are considering outlier. Okay, for small sigma, we are considering the outliers. For to handle the outlier, we have to for sigma. Okay, we see this RBF function. So it is total depend on data sets how to choose the proper sigma then to handle. So it is same as also formula is same as KNN with small k. You just remember the previous in KNN. We have seen that in KNN with small k, both the things are same. Is both the things. So the last thing is bias variant trade-off. Bias variance trade-off. So if you remember, we have parameter hyperparameter C for our loss functions and the hyperparameter sigma for the RBF function. Two functions is elastic. So if we increase the value of the C, then we are going to overfit our model. We are simple going to overfit our model. This means what? This means we are making the high variance. And if we decrease the value of C, then we are going to make the underfit model. This implies that we are going to a high bias model. We are going to make the high bias model. This is the thing. And sample we see RBF SVM. See, remember the RBF radial basis function SVM. Then there we have two parameters C and mu, and this C is coming from our loss functions hyperparameter, and this C is coming from our RBF. Just I am going to remember this kind of. And now the third thing, this is the sixth, this will be seventh. Now the seventh will be for large D. If our data set belongs to a high large dimension, in such situations, if we have the large D, then in such situations what happen? In such situations for large D, SVM are very good because we see for a cardinal RBF where we are going to transfer our original dimensions data point, dimension of original set of data point for for another set of another dimension in our in the dimension size increase. So SVM is very good to handle the large dimension. very good for for large time. For SVM is very good for large one. We see this thing in kernel dimension. Just remember the kernel tree of radial basis functions seen there. We are seeing that when we are converting our data sets to d dimension to d dash dimension, then so simply d is smaller than our d. We also see this. Now we are discussing two things, that is best case and worst. First we best case. Best case. What is the best case? Best thing of our SVM? What is the best thing? The best thing is here that to choose the right kernel. Best thing is to choose the right kernel is the best thing. Okay, and the worst thing is that, and the worst thing, if you see the worst case of the SVM, then if we have a large number of our training number of data sets in data set is large, is very large. Mainly we see in internet based company. Mainly if we focused on internet based company, then we see that then in such our number of data set is very large. Okay, number of data set is very large. So in such cases, the training time complexity is very, in such situations the training time complexity, because of this training time complexity is very high. So in such scenario we cannot use the SVM, because in such training time complexity so high, in such situations SVM is not applicable. Okay, and also if you see our k means number of support vector, if our number of support vectors, if our number of support vectors is k, okay, and k is large, and k is large, so in such situations low latency, build the low latency model to build a low latency model is not, because we see that if you just consider the dual problem, then the number of training data sets is totally depend on our number of, if our support vector is large, then low latency build. Okay, I think these are the thing, these 9 things are really happen in real world. So to build a model using simply SVM, have to have to take care about this, when we have to using the features transformations, and what in what situations which decisions surface most important, and what kind of similarity function we have to is choosing the similarity function, what kind of parameters, that is sigma, we have to choose. The interpretability is not possible through this one, but if you use simple forward feature selection methods, then we can, if you invest some time, then it is possible. And the outlier very it is very little impact, very good for outlier handling, and for outlier handling, it is SVM technique is very very good, and it is very little impact to our outlier. And the main thing is that, and by simple RBF, if you choose RBF kernel, then simple by handling the parameter sigma, we can easily handle the outlier impact. We can easily handle, and also small sigma are more prone to impact the outliers. And we see this thing in KNN for small k also. And bias variable transfers, we see that if we increase the value of our parameter c, that is coming from our loss functions, then our model will more prone to our high to make a high variance model. If we decrease the value of c, then this model is going to underfit model. Okay, so how to choose a proper, how we choose a proper c and sigma, that we also see in when we are in logistic regression, when we are seeing the grid search technique and the random search technique. By simply using these three, we can easily choose c and sigma. And also we see that for a large dimension is very good, SVM is very good because of kernel trick, because of when using the RBF kernel trick, then we can see it is easily it is handle the large dimension of. And also best case for the SVM is that is the right kernel. Okay, this is the main best important thing. And we have to the worst case. Worst case is that our the number of data set very large. That will mainly see in the mainly internet based company. We see that our number of data sets in such scenario is very. So in such situations, the SVM is not applicable. As well as our number of dimensions as a support vectors. If our support vectors is large, then we cannot as well build the low latency, because it is not possible. At the end of the day, if we remember the dual problem, in dual problem we see that in dual problem we see um, the actually the FQ function that we call our query function. Actually query function, if we just recall the query function that will coming from our dual problem, it is totally dependent on our support vectors only. Okay, so because of that, if our support vectors number of support vectors is large, then it is not possible to build a low latency. So to build a support vectors, basically we have to we have to think about this matter. Okay, I think till now we have completed this 14 lecture. I think in 14th lecture I will cover everything about the SVM. Although if you have any doubt, if you have any suggestions, this kind of what is our how to extend this series of lectures, please suggest me, and then I'm adding some lectures on SVM. Okay, thank you. Now we will see in next series of lectures.